I or love. AI, the next frontier. Hi friends, welcome to Xiaol.x. Are you ready for a story? Today, we explore the giant computer brains become super smart and do amazing tricks. Did you know computers have giant invisible brains? It's true, but just like you go to kindergarten, these robot brains need to go to school too. Without a teacher, they don't know anything. They need a mission to get smarter every day. But the first teacher, named Muon, was very clumsy. Imagine trying to fix a delicate, tiny watch with a giant, heavy hammer. Smash! It failed. He used the wrong tools, and the poor robots got confused and made big, messy mistakes. Luckily, the new supercoach has a secret: magic earplugs. When the computer makes a loud, screaming mistake, the coach turns the volume down. Shh! It ignores the scary noise so the robot can fix the problem peacefully and learn the answer perfectly.
Welcome to the Deep Dive, the place where we take stacks of complex sources and distill them into genuinely useful knowledge. Today, we are undertaking a mission that sounds like science fiction, but is happening right now, teaching the biggest, smartest digital brains on the planet. I'm talking about the large language models that power everything from search to creative writing.
And these LLMs, they're so complex. They don't just spring into the world fully formed. I mean, they're built on these massive architectures, sometimes with trillions of connections or what we call parameters. To learn, these giant brains really need structure.
And when you're dealing with a brain of that scale, you can't just, rely on trial and error. You need a dedicated instructor, a specialist who can observe every single mistake the brain makes and then tell it exactly how to adjust its wiring to get better next time.
And that instructor is called the optimizer.
The optimizer. Think of it as the ultimate learning coach for a digital genius.
Exactly. And our sources today, they point to a fundamental breakthrough in this coaching process. We're going to be digging deep into a new, vastly improved supercoach called ROOT. That stands for Robust Orthogonalized Optimizer.
The name itself kind of gives away, doesn't it? Its goal is to make the learning process precise and, well, unshakably stable.
Right, because we need a new coach. The old ones, even good ones like Adam or the more recent Muon, they're starting to fail, especially when the brains get truly enormous and sensitive.
So our mission today is to unpack how Root uses two major customized tools. It's like a precision tuning kit and a genius noise filter. And these are designed to fix two specific flaws that plague large AI systems, helping them learn faster, more reliably, and just get smarter results than ever before.
We're basically offering you a shortcut to understanding the cutting edge of AI training. So let's start at the beginning. What is the core job of the optimizer, and why did the previous coaches start to struggle?
Okay, let's unpack this. So if an LLM makes a mistake, the optimizer gets a report. What is that report, scientifically speaking?
That report is a gradient. It's a mathematical signal that tells the coach how far off the mark the brain was on a particular task. The optimizer then takes that gradient and generates an update, a specific instruction telling the brain how to change its internal connections or parameters to do better next time.
So if the brain is trying to write a sentence and uses the wrong verb, the gradient is the error note. And the optimizer says, okay, next time, shift this internal connection slightly to favor this other verb.
That's it, exactly. And for years, we used simple coaches like SGD or Adam. They were fine, but, slow, a bit redundant. As models became colossal, they needed a smarter, more efficient coach, which is what led to Muon.
So what made Muon so smart? What was its big trick?
Muon introduced a technique called orthogonalization. Now, to get this, think about the brain's connections not as single wires, but as vast organized groups, which we call weight matrices. If a coach is giving advice on how to adjust those groups, simple optimizers might give overlapping advice. It's like telling the brain to practice drawing lines and then also telling it to practice drawing straight lines.
Redundant effort.
Precisely. Orthogonalization is like making sure every single piece of advice the coach gives moves the brain in a totally new and unique learning direction. So one piece of advice is about drawing circles, the next is about shading, the next is perspective. This prevents the brain from getting stuck in a rut, and it ensures efficient use of learning time.
So if I'm hearing you right, the whole point of orthogonalization is to reduce that redundant effort and just increase the diversity of the learning direction.
That's the high-level takeaway. And it helps a lot, but even this smart coach, Muon, it ran into two major roadblocks that Root was specifically engineered to overcome.
And what were these two fundamental flaws?
Well, the first was dimensional fragility.
Dimensional fragility.
Yeah, it means the quality of the coaching suddenly got inconsistent, depending on the shape and size of the group of connections it was tuning. The tools literally broke down on certain parts of the brain.
And the second flaw.
Outlier-induced noise. This is less about precision and more about stability. The coach would get easily distracted, totally overwhelmed by sudden, massive errors. Just a few screaming mistakes that poison the entire lesson plan.
Okay, so Root has a fix for both. Let's tackle that first one. Dimensional fragility. The idea that the coaching breaks down based on the shape of the layer. I'm picturing a massive construction project. You have to tighten bolts on hundreds of thousands of components, but they're all different shapes. Some are long, narrow rectangles, some are perfect squares.
That's a great analogy. And Muon, the previous coach, used a one-size-fits-all wrench to adjust all those components. The sources call this using fixed coefficients in the calculation.
And what happens when you use a fixed wrench on a bunch of different shapes?
Well, it works okay for some of them, the narrow rectangles, for example. But our source material shows it failed, and failed miserably, on specific shapes, particularly layers that were perfect squares. Things like a 2048 by 2048 matrix, which you find right in the core of these LLMs.
So what was the consequence? What happened when you used the wrong-sized wrench on that square part?
Extreme imprecision. The error in the adjustment, what we measure as the mean squared error, or MSE, it was shockingly high for that specific layer. It came in at 0.0499.
That sounds like a really small number, but I'm guessing in this world it's not.
It's not at all. When you're adjusting trillions of connections, that imprecision just compounds and compounds. It means that specific critical layer was getting fragile, poorly tuned advice.
And that inefficiency, that inaccuracy, it must really slow down or even hurt the brain's development.
It creates a bottleneck. If one part of the brain is getting shaky advice, the whole system suffers. And this is where Root steps in. It fixes this with a specialized mechanism called adaptive Newton iteration, or AID-Newton.
AID-Newton. So this is the custom toolkit. How does it work differently?
Well, Root realizes that a fixed coefficient is just a bad idea. So AID-Newton introduces dimension-specific coefficients. Instead of one wrench, Root uses this iterative process, that's the Newton iteration part, to calculate and generate the perfect custom-sized wrench for every single unique size and shape of layer in the LLM.
So it's not guessing, it's dynamically calculating the exact optimal tuning needed, whether it's for that tricky 2048 by 2048 square or some long, narrow rectangle.
Correct. The adaptive part means the tool automatically calibrates itself. It ensures every single layer receives precise, high-quality advice. This is foundational robustness, making sure the tool doesn't break.
And we have proof of this precision, right? What happened when they applied Root's custom tool to that same tricky square matrix?
The error dropped significantly. That high error of 0.0499 from the old wrench, it came all the way down to just 0.0352 using Root's adaptive system.
Wow, that's cutting the error margin by nearly a third just by having the right tool for the job.
Right. It's a huge gain. And the sources showed this wasn't a one-off fix. Throughout the entire training process, Root consistently maintained a lower relative error compared to the Muon baseline. The coaching quality was just superior, full stop.
Which means the quality of the updates is uniform across the whole structure. No more weak links.
Exactly. No more fragile components in the digital brain.
Okay, now let's move on to problem 2. The noise. Outlier-induced noise. This sounds like the digital equivalent of trying to study for an exam while someone is screaming right next to you.
That is a perfect analogy. In large-scale training, with these massive data sets, occasionally one piece of data is just wildly wrong or a calculation goes haywire. This creates an anomalously large gradient, that screaming mistake we mentioned earlier.
And what happens when the computer brain hears that screaming mistake?
Oh, the stability of the entire learning process can just shatter. The model gets a feedback signal that is exponentially larger than normal, so it overcorrects violently. The source material talks about severe consequences, like exploding attention logits.
Okay, we need to unpack that for our listener. What does it mean for the brain to have exploding attention logits?
It means the brain temporarily goes haywire. The internal mechanisms it uses to decide what information is important, its attention, suddenly receive an overwhelming shock. It's like the brain stands up, yells, and forgets all its previous lessons for a moment just because of one loud piece of data. It completely destabilizes everything.
So Root needs some industrial-strength earplugs to block out that screaming mistake and protect the real lesson.
Precisely, and that's Root's second major feature. Proximal optimization via soft thresholding. It applies a mathematical noise filter to the error report before any of the delicate tuning starts.
How does that filter work? Does it just chop off the biggest errors?
Not quite. It's more elegant. It models the incoming mistake as two parts. The core, useful lesson, we'll call that the robust base component, and the unnecessary outlier noise. Soft thresholding is all about identifying that noisy screaming part and smoothly shrinking its magnitude until it's harmless.
Why is smooth, shrinking soft thresholding better than just abruptly chopping off the top of the mistake? I know older methods like hard clipping did that.
It's crucial because with hard clipping, you lose resolution. You chop off the top of the error, but you also destroy the subtle relative importance of the good information that was near that cutoff. Soft thresholding applies a continuous curve of shrinkage. It dampens the truly extreme values, but it preserves the overall shape and direction of the useful signal. It keeps the quiet, consistent lessons intact.
That makes perfect sense. It's about protecting the signal, not just destroying the noise. And the researchers figured out the sweet spot for applying this filter right.
They did. They optimized it very carefully. They found the ideal balance, the optimal equilibrium between filtering noise and retaining good information, occurs when the coach shrinks anything above the 90th percentile of the gradient magnitudes.
So, to put that simply, in any batch of learning, they look at the top 10% of the loudest, craziest mistakes and just turn their volume way down. And that allows the quiet, consistent lessons from the other 90% of the data to actually get through.
That's the practical implication. By focusing the filter only on the extreme outliers, Root ensures stability without corrupting the actual learning signal.
This is really a beautiful piece of engineering. You have these custom dimension-specific tools for extreme precision with Ada Newton, and then you combine it with this high-tech noise filter for total stability with soft thresholding. But, I mean, the only thing that really matters is the report card.
Yeah.
Did all this complex tuning actually make the LLM smarter?
Absolutely. The experiments in the source material translate this dual robustness directly into superior performance. Let's look at the foundational training first.
The pre-training phase, where the brain is just absorbing massive amounts of raw text.
Yes, in the pre-training experiments on 10 billion tokens, the full root optimizer achieved the lowest final training loss. It was 2.5407, which measurably surpasses the Muon baseline.
For listeners who might not know, what does a lower training loss like 2.5407 tell us in practical terms?
It means that at the end of that foundational learning period, the digital brain had a higher quality, more accurate, more comprehensive understanding of the data than any previous coach could deliver at that same point. The learning was just more efficient and more thorough.
And a better foundation should lead to better test scores, what we call generalization. So how did Root do when they asked the LLM to solve problems it hadn't seen before?
It showed superior generalization across a whole suite of academic benchmarks, things like HelloSwag and BoolQ. Root achieved a superior average zero-shot performance of 60.12%. Muon, the previous best, was at 59.59%.
That half a percentage point increase in this field, that's actually huge. It proves that the LLM, thanks to Root, is demonstrably smarter and better at reasoning through new challenges.
And what's also fascinating is that the benefits weren't just for language, the soft thresholding noise filtering trick. It proved beneficial in completely different types of AI, like those designed for vision.
Like teaching a vision transformer, a VIT, how to classify images instead of text.
Exactly. When they were training a VIT on image datasets like CFAR10, adding Root's soft thresholding mechanism significantly mitigated that gradient noise. In one trial, the image classification accuracy boosted all the way up to 88.44%.
That just shows that the need for robustness and stability is universal, isn't it? Whether the brain is learning language or learning to see, if the coach is distracted by noise, progress is going to be hampered.
I think this work really establishes a major new paradigm. We've shown that dual robustness is the key. You have Ada Newton providing this extreme dimension-specific precision and soft thresholding providing total stability by filtering noise. This combination ensures that as these AI systems scale up, the training process doesn't become prohibitively slow or, prone to catastrophic failure.
It's amazing how much difference optimizing the coaching process makes. We learned today that even at the immense scale of LLMs, tiny details matter, like having the exact right custom-made tool for every single connection. The pursuit of stability and precision is really what unlocks the next generation of intelligence.
Indeed. It also raises the question of how we, as humans, optimize our own learning environments. We've seen how crucial it is to custom-tune learning advice and to filter out noise effectively.
So for you, our listener, who is now vastly better informed about the future of AI training, if you were designing your ultimate personal learning coach based on these principles, a coach for your own brain, what is the one noise filter you would use or design to help you concentrate the absolute best in your everyday life? Something to ponder as you tackle your next deep dive.